I would like to invite Professor Ze'ev Nutov, who will chair the first session.
I'll introduce the first talk is by Amit Daniely, and he's currently doing a PhD at the Math Department of the Hebrew University of Jerusalem. His advisor are Nati Lineal and Shai Shalev-Schwartz. His main field of interest is statistical and computation learning theory. He's got a best student paper wrote at COLT 2011 and the Google Scholarship. And today he will talk about his joint work with Nati Lineal and Shai Shalev-Schwartz. So, Amit.
So first, thank you for the invitation and the opportunity to be here. So the starting point of this project is that today, after 50 years of research in machine learning and after 30 years of research in machine learning from a computational point of view, we still don't know to show that the most basic problem in learning theory that we think that are hard are indeed hard. And moreover, there is currently only one known technique to do so. And in this work, we develop a new technique to prove hardness of learning problems. So I'll start by giving a quick introduction to machine learning in general and more concretely to the PAC model of learning. Then I'll try to explain why is it that hard to prove hardness of learning problem. I'll very briefly describe the old technique, the cryptographic technique, and then I'll introduce our new technique and show you some application and some stuff we plan to do in the future. Okay, so let's start with explaining what is machine learning. And more concretely, I'll talk about classification. So in the classification problem, we want to learn a function which we denote by f star from some domain x that is called the instance space to another domain y that is called the label space. For example, here is a typical task in machine learning. You want to learn a function that distinguishes between images having the digit 3 in them and images having the digit 5 in them. So this is how it works. We have a labeled sample. We have a collection of images, each of which is labeled by 3 or 5 according to the digit appearing in it. We feed this collection to some algorithm, to some learning algorithm. Then it do something and return a function from the collection of images to 3 and 5. And hopefully, the function h returned by the algorithm is close in some sense to the function we're really interested in, which is f star. Okay, so let's try to analyze this problem. So we assume that there is some unknown function f star from the domain x to 0 and 1. Here we talk only about binary classification when there are only two labels, 0 and 1. So we have a function f star that we want to learn, and we also assume that there is some unknown distribution d on the instance space x. So in the previous example, you should think of d as the distribution from which the images are sampled. So this is the real distribution on the world, on our world. And in this talk, we'll confine ourselves to the case where the instance space is the Boolean cube in n dimension, and n will be our complexity parameter. We want the algorithms to be polynomial in n. Okay, so the objective in classification is based on samples of the form x, f star x, where x is sampled from d, to find a function from x to 0, 1 with a small error. And here the error is defined as follows. The error of the function f with respect to the distribution d is the probability that f of x is different than f star of x, where x is sampled from the distribution d. So based on such samples, we want to find a function f that have a small error. Okay, so ideally we would like an algorithm with the following guarantees. For every function f star and for every distribution d, it runs in time polynomial in n and guaranteed to return a good function with high probability. However, it is not hard to see that even if we ignore a computational aspect, then no such algorithms exist. For example, in order to describe a general function from the Boolean cube to 0 and 1, even approximately, we need about 2 to the n bits, and there is no way to decipher these many bits from polynomially many samples. Okay, so the inevitable conclusion is that we have to make some assumption on either F star, the learned hypothesis, or the distribution D. And this leads us to the notion of hypothesis class. This is a very popular type of assumption that stands behind the PAC model that we'll introduce in the next slide. So we assume that there is a predefined hypothesis class H. H is a collection of functions from x to 0 and 1. And our only assumption is that the learned function f star comes from this class. Okay, we make no assumption on the distribution D. And we assume that the function f star comes from the class H. And the point is that if H is small enough, then at least if we ignore computational efficiency, then it is possible to learn a function from this class. And the computational question whether we can do that efficiently becomes meaningful. Okay, so let's introduce that more precisely. So this is the PAC model. It was introduced by Valiant in '84. And till today, this is the basic model in which machine learning and more particular classification is studied in theoretical computer science. So a learning problem is defined by a hypothesis class H. Whenever you give me a hypothesis class H, it's defined a learning problem. We will not concrete hypothesis classes by informative names like half spaces, DNF. I'll introduce those classes in the next slides. The input to the learning algorithm is an error parameter epsilon and an oracle access to random examples of the form x, f star x, where x is sampled from some unknown distribution D, and f star is some unknown function from H. And the output of the learning algorithm should be, with high probability, a function f from the Boolean cube to 0, 1, or more correctly, a description or polynomially sized description of such a function with error less than epsilon. And I emphasize, and this will be very important in this talk and generally in this project, that the learning algorithm have the freedom to return a function that does not belong to the learner class. If the algorithm chooses to do so, we call such a learner improper learner. If the learning algorithm is guaranteed to return a function f from H, we call this learner a proper learner. And the reason it is so important is that this is exactly the point that makes it so hard to prove a hardness of learning problem. So we'll talk more about it later. And finally, I say that an algorithm is efficient if it runs in time polynomial in n and 1 over epsilon, and it returns a hypothesis that can be evaluated in time polynomial in n and 1 over epsilon. Okay, so what are the basic learning problems that we're interested in? Maybe the most basic problem is the problem of learning half spaces. Here we look on the following function. For every vector w in Rn, we define a function from the Boolean cube to 0 and 1 as follows. H of x is the sum of the inner product of w and x. Okay, so this is a function such that the pre-image of 1 is a half space. Okay, so this is a very popular class, both in theory and in practice, and we know a lot about this hypothesis class and the corresponding learning problem. A natural generalization of this class is learning intersection of half spaces. So here we look on a function from the Boolean cube to 0, 1, such that the pre-image of 1 is an intersection of several half spaces. So this is another very popular class. And the last family of hypothesis classes or learning problems I'll describe are circuits and DNF formulas. So we denote by circuits of k for a constant number k, the class of function from the Boolean cube to 0, 1 that can be realized by a circuit of depth k and size polynomial in n. And of particular interest in machine learning is the class of DNF formulas, which is simply the class of circuits of depth 2 and polynomial size. Okay, so this is maybe the 3 most basic hypothesis classes in machine learning, and let's see what do we know about these classes today after 30 years of research. So let's start with something we do know. We do know that we can learn the class of half spaces efficiently. We know that already from 30 years, almost 20 years before the introduction of the PAC model. Okay, but what happens if we go a bit further? If we look on DNF or circuits, then the best known algorithms are unable to learn even DNF formulas, which are depth to circuits, and not even decision trees, which are a subclass of DNF formulas. On the other hand, the best known lower bounds, proved by Haritano in '93, under cryptographic assumption, only shows that it is impossible to learn circuits of constant depth for some unspecified constant. So this is very far from DNF. This is a much, much richer cluster than DNF formulas. For intersection of half spaces, the best known algorithms are unable to learn even intersection of two half spaces, whereas the best known lower bounds, again, under cryptographic assumption proved by Clivans and Shrestov, only show that it is impossible to learn intersection of polynomially many half spaces. And finally, if we go back to half spaces, but we look on this class in the so-called agnostic model. So the agnostic model is a variant of the PAC model when some errors are allowed. I won't define it, but I'll make two remarks about it for those who know. So for here, the best known algorithms have terrible approximation ratio, whereas the best known lower bounds only rules out exact learning. Okay, so for most of the basic classes, we don't know whether they are hard or whether they're easy. For all these classes, we think that the learning problems are hard, but we don't know to prove this. Okay, so next I'll try to explain why is it so hard, and specifically, I'll try to convince you that standard reductions from NP-hard problems do not seem to apply in this context. But I'll start with something we do know to do. We do know to prove hardness of proper learning. So I remind you that a learning algorithm is proper if it is guaranteed to return a function from the learned class H. Okay, so I need one simple definition. We say that a sample collection of pairs xi, yi, where xi is in the Boolean cube and yi is either 0 or 1, is realized or realizable by the hypothesis class H if there exists some h such that for every I, h of x, y equal to yi. And the hardness of proper learning of the problem corresponding to h is usually established based on the hardness of this problem. This is the problem of distinguishing realizable from unrealizable samples. So the input is a sample, and we should decide whether the given sample is realizable or not. Okay, so this is a computational problem. Sometimes it's easy, sometimes it's hard, and if it is hard, we might get lucky, and we usually get lucky, and we're able to show that it is hard by a reduction from some NP-hard problem. And why is it so important? Because of the following quite simple theorem that tells us that if it is NP-hard to distinguish realizable samples from unrealizable samples, if it is hard to solve this problem, then no proper learning algorithm can learn H efficiently unless NP equal to RP. Okay, so I'll show you the proof of this theorem. First, because it is a simple and nice proof, and second, because our proof is a variant of this proof. So we assume that the problem of distinguish realizable samples from unrealizable samples is hard, and toward a contradiction, I assume that there is a proper learner A that learns the class H efficiently. And I'll drive a contradiction by showing you that we can find an algorithm that distinguishes realizable from unrealizable samples. So given a sample, we will simply run the algorithm A on this sample and obtain a function f. And what do I mean by that? We give the algorithm an error parameter epsilon, which is 1 over 2m, where m is the number of examples in our sample. And whenever the algorithm asks for a random example, we simply choose uniformly at random from the examples in the sample S. Okay, so we run the algorithm this way. It will return us some function, and then we will check. If for every I, f of xi is yi, we will say that the sample is realizable. Otherwise, we will say that it is not realizable. Okay, this is very simple algorithm. And why does it work? If S is realizable, then since the algorithm A learn the class H, it is guaranteed to return a function with error less than 1/2m, which is it not hard to see that it entails that for every I, f of xi is yi, and in this case, we will indeed say that the sample is realizable. So note that so far, I did not use the fact that the algorithm A is proper, only the fact that it is efficient and it learns the class H. And I use the fact that it is proper in the last point. So if the sample is not realizable, then the algorithm will do something. I don't care what it will do, and it will return to me some function H that I know it belongs to H. Now, since the sample is not realizable, it tells us that there is some I such that H of xi is different from yi, and we will say that the sample is unrealizable. So that's how we can solve this problem. So not two things. The first is that, as I said, here we relied crucially on the fact that the learning algorithm is proper. And the problem is that an improper algorithm might perform well even if the sample is unrealizable. And what we will do in our new techniques is to rule out the possibility that even proper algorithm will perform well on unrealizable sample. Okay, so the argument, as we say, don't work for improper learnings, but you can tell me, okay, so maybe there is a more clever way to show hardness of learning problems based on P is different than NP. So here I can say that no one succeeded to do so during the last 30 years. And second, a recent result of Applebaum, Barak, and Xiao tell us that hardness of learning or hardness of improper learning cannot be derived by so-called standard reductions from NPR problems unless the polynomial hierarchy collapses. So they defined a class of standard reduction, and they show that unless the polynomial hierarchy collapses, there is no way to reduce an NPR problem to the problem of learning some hypothesis class. And the conclusion is that at least until some major changes happens in complexity theory, we must rely on other possibly stronger assumptions than P is different from NP in order to prove hardness of learning problems. So this leads us to the next part when I describe the cryptographic techniques. So this is currently, before our technique, the only known technique to prove hardness of learning problems based on cryptographic assumptions. So I'll describe that very, very briefly, just to give you a rough idea. So it was introduced by Kearns and Valiant 5 years after the introduction of the PAC model. The idea is quite simple. We start with a collection of one-way trapdoor permutations. This, by standard arguments, yields a usually artificial hypothesis class H prime that it is hard to learn, and then we reduce this artificial class to an interesting class H, and the conclusion is that the class H is not learnable. Okay, so this argument yields virtually all known lower bounds for learning problem, and as I said a few minutes ago, these lower bounds are very far from the performance of the best known algorithms. This is about improper, yeah, where the conclusion is that H is hard to learn even by an improper algorithm. And when I say hard to learn, I mean hard to learn even by improper algorithm. Okay, so that's all I say about this technique, and now we introduce our new technique. So I remind you that in order to prove hardness of proper learning, we showed that the problem of distinguishing realizable from unrealizable samples is hard. And the argument failed for improper learning due to the following fact. That improper algorithm might perform well even on unrealizable samples. And the key observation that stands behind our new technique is that even improper learning cannot perform well on very random sample. So next I'll define precisely what do I mean by very random sample. But if this key observation is true, then the conclusion is that we can use the argument I showed before in order to show that if it is hard to distinguish realizable from random sample, then it is hard to learn H even by improper algorithm. Okay, so what do I mean by very random? So intuitively, a sample S is very random if the following hold for every every function f is likely to make a lot of errors on this sample. So let's see a simple example. Suppose, for example, that all the examples in S are uniform and independent from one another. Then it is not hard to see that if this is the case and we take a function f, then with very high probability, with probability of 1 minus 2 to the minus m, it will make more than m over 100 errors. So we'll try to formulate this property. We'll define the error of function f with respect to a fixed sample s as the average number of mistakes f does on this sample. And here comes the definition. We look on a distribution S that generates a whole sample. So not that the distribution S don't generate a single example like most of the distribution in this context do, but it generates a whole sample of M examples, and the different examples might depend on one another. Okay, so I have some distribution like this that generate sample, and we say that it is Q scattered or Q random if the following holds. For every function you fix from x to 0, 1, if you sample or you draw at random a sample from the distribution S and look on the error of f with respect to that sample, then with probability of greater than 1 minus 2 to the minus q, it will be more than 1%. Okay, so again, we have a distribution that generates a whole sample. We say that it is Q scattered if the following experiment succeeds only with probability less than 2 to the minus q. We fix any function f you want, then we draw at random a sample, we look on the error of f on this sample, and if it is less than 1%, the experiment succeeds. Okay, so that's the definition. And our basic theorem talks about this problem. So this is the problem of distinguishing realizable from S random sample, and S, again, is a distribution that generates a sample. So the input is, again, a sample, and now we have a promise. The sample is either realizable or randomly chosen from the distribution S. And the output is to decipher whether the sample is realizable or unrealizable, or sampled from the distribution S. And the basic theorem tells us that if this problem is hard and the distribution S is Q scattered, then any efficient algorithm that learns H must use at least Q over N samples. And the immediate conclusion is that if for every polynomial Q, there is a Qn scattered distribution S for which this problem is hard, then it is hard to learn H efficiently. Okay, that's all. So I won't describe the proof in detail, but I'll try to explain you the idea. So the point is to prove the Q observation that even improper algorithm cannot perform well on very random or very scattered sample, and after we show this Q observation, we can simply use the argument we showed in the beginning. So the point is that if A is an efficient learning algorithm, it uses only polynomially many examples. And therefore, at least if it's deterministic, if it's not, we use a variant of this argument, but if A is deterministic, then the hypothesis A returns depends only on polynomially many samples, and therefore the number of hypotheses A might return is not too large, because we can describe each of them by a string which is of polynomial size. Now, since the sample is very scattered, for every hypothesis A might return, will have a large error with very high probability, and since this number of hypotheses is not that large, by a simple union bound, we conclude that A will return a bad hypothesis. All these hypotheses will be very bad. Okay, so that's all. If you put the number, you get the theorem I've stated in the previous slide. Okay, so that's the technique, and in the next part, I'll describe what we know to prove to prove based on this technique. But we'll have to start with some hard problem. We have to start with some problem that it is hard on average to reduce from. And the problem that we start with is the problem that we will introduce Feige's assumption that give us such a problem that is conjectured to be hard. Based on Feige's assumption, we will show our first application. This will be very brief. Then we will generalize Feige's assumption and get a stronger assumption and show other applications based on this assumption. So let's start with Feige's assumptions. He talks about random three-sat formulas. So I guess that all of you remember what is a three-sat formula. It's simply a collection of three-sat constraints. We will denote by n the number of variables and by m the number of constraints. We define the value of a formula J as the maximal fraction of constraints that can be satisfied by a single assignment. And as usual, if the value is 1, if you can satisfy all the constraints, we say that the formula is satisfiable. And another basic fact that we will need is that for every formula have value at least 7 over 8. You can get this value by a random assignment. And if the formula is large and the constraints were chosen uniformly at random, and the number of constraints is at least 6n, even 5 will work here, then the value of j is not only greater than 7 over 8, but it's also smaller than 7 over 8 plus a little o of 1. So the point is that for a random formula have a value of approximately 7 over 8 with high probability. So the problem Feige looked at and many other people looked at is the following. It is the problem of distinguishing satisfiable from random three-sat formulas. So it has a parameter, a function m of n. The input to this problem is a three-sat formula with n variables and mn constraints. And again, we have a promise. Either the formula is satisfiable or it is random. And we need to decide whether the formula is satisfiable or random. So this problem has been studied extensively since the 60s, and it is not hard to see that it gets harder as m, the number of constraints, get smaller as long as it is greater than 6n. Because if you have more constraints, then it should be easier to show that the formula is not satisfiable because there is more ways to reach contradictions. And the currently best known algorithms by Feige and Ofek only succeeds, the best known efficient algorithm only succeeds if the number of constraints is at least n to the 1.5. Okay, so based on that, Feige in 2002 made the following assumption. It assumed that for every constant c, which is at least 6, the problem of distinguishing satisfiable from random formulas with at least cn constraints is hard. Okay, so he made that assumption, and based on this assumption, he showed the hardness of approximation results that do not, at least at that time, no one knows to prove them based on p is different from np. Okay, so this is the assumption we rely on, and there is plenty of evidence to this assumption. So one evidence is the PCP theorem of Hasted, and I'll formulate it in a non-standard way. It tells us that it is NP hard to distinguish satisfiable from semi-random formulas. So what do I mean by a semi-random formula? A semi-random formula is a formula that it is not at all random, but its value is approximately the value of a random formula. So Hasted theorem tells us that it is NP hard to distinguish satisfiable from semi-random formula, and therefore Feige's assumption is a generalization, strengthening of this theorem. This is one evidence. The second evidence is, of course, the performance of best known algorithm, which is very far from what predicted by this assumption. And lastly, we also have concrete lower bounds via resolution lower bounds on the performance of a large class of algorithms. So for each algorithm of the so-called Davis-Putnam style, we know that its running time is provably, or the number of constraints you have to see in order to succeed is probably at least n to the 1.5 minus epsilon. Okay, so we'll need that when we'll try to generalize this assumption. So based on this assumption, using our technique, we can show the following result. This will be some kind of appetizer because we don't talk about definite hardness, but it just shows that we need many samples. So we are in the situation when we are trying to solve some statistical problem or some learning problem, and we have a lot of data, much, much beyond what is statistically needed in order to solve the problem. And a natural question is, in this context, is whether we can do something with this seemingly redundant data. And more concretely, can we use this more data in order to speed up computations? So this question arose a lot of interest recently due to the fact that these days we have a lot of available data. And using the technique I presented and based on Feige's assumption, we can show the first positive answer to this question for a natural classification problem. So I won't describe the problem. It's called the problem of agnostic learning of half spaces over sparse vectors. Okay, so in the next part, we try to get strong result. In particular, we want to show definite hardness of learning problems and not conditional hardness only if we have a limited sample. And at least today, we still don't know to prove it based on Feige's assumption, and we need a stronger assumption. So I'll try to motivate such an assumption. So we want to generalize Feige's assumptions in two aspects. First, we want to generalize it to constraints other than 3SAT, to more general predicates. And second, we want the number of constraints to be much larger than linear in n. Okay, so the problems we look at are random CSP problems defined by a single predicate P. Okay, so P is any function from -1,1 to the k to 0, 1. For example, the predicate corresponding to the 3SAT problem is this one. A P formula is simply a collection of P constraints. For example, here J is a P formula, and as usual, we want to find an assignment to the variables that maximizes the number of satisfied constraints. As before, we can define the value of J as the maximal function of constraint that can be simultaneously satisfied, and we say that this formula is satisfied if its value is 1. And the last fact we will need is the following. For every predicate P, there is a constant, that I called it here V of P, that depends only on P, such that the following holds. For if the formula J is random and it has a superlinear number of constraints, then its value is approximately this value with high probability. Okay, so we look on the problem of distinguishing, maybe I'll talk about it before, so in the next slide, we will consider the problem of distinguishing random P formula from satisfiable P formula. And the next assumption try to predict when this problem is hard. So in order to reach a plausible assumption, let's try to recall the evidence to Feige's assumption and try to keep this evidence also for our assumption. So the first evidence was that it is hard to distinguish satisfiable from semi-random formula. We'll keep this evidence also in our assumption. The second or the third evidence was lower bounds, resolution lower bounds on a large family of algorithms, which tell us that we need at least n to the 1.5 many constraints, so we'll try to keep this one too. And we had another evidence, which is the performance of the best known algorithm. So here we don't have this evidence because it is not the case that each and every predicate has been studied, of course. Okay, so here is the assumption. We assume that for every d, there is k. Think of k as much, much larger than d. Say 2 to the d, or 2 to the 2 to the d, or as large as you want, such that the following hold. For every predicate p satisfying the following two conditions, first, it is an NPR to distinguish satisfiable from semi-random formulas. And second, any Davis-Putnam algorithm must see at least n to the k random constraints in order to succeed. So if these two conditions hold, we assume that distinguishing satisfiable from random P formulas with n to the d constraint is hard. Okay, so let's read it from bottom to top. We look on the problem of distinguishing satisfiable from random P formulas with n to the d constraint. And when will we say that this problem is hard? First, when it is hard to distinguish satisfiable from semi-random formulas. And second is that any Davis-Putnam algorithm that we will apply on this problem will need many more constraints than n to the d. Okay, so this is the assumption. It is a strong assumption, I admit it. And in the last slide, we'll talk about some future work and possibilities to prove the result I present based on less strong assumption, on weaker assumptions. D is a constant. The arity is k. The arity is k. No, I use it k for the. The arity is not mentioned in this assumption.
So how is D? What's D?
We fix D. Okay, we fix D, and we look on the problem of distinguishing random P formulas with. I mean, we fix D, and after that we try to find predicate for which this problem is hard. I mean, we fix D and we fix a predicate, and we look on the problem of distinguishing random formulas with n to the d constraint from satisfiable constraint. Okay.
N to the d is the number of constraints in your system.
Yeah, n to the d is the number of constraints we have, the number of random constraints we see. Okay, so what can we show based on this assumption? We start with the problem of learning DNF. So in the first paper about the Park model, Valiant showed that it is for every constant Q, it is possible to learn DNF formulas with Q clauses in polynomial time, in time n to the Q. Okay, so it's polynomial for every constant Q. And under our assumption and using our technique, we're able to show that for any super constant Q, learning DNF formulas with Q clauses is hard. So Valiant's algorithm is quite tight. And an immediate corollary of this theorem is that, again, under our assumption, under the strong random CSP assumption, it is hard to learn DNF formulas of polynomial size. Okay, so I won't talk about the truth, but as you can guess, the idea is to reduce the problem of distinguishing satisfiable from random formulas to the problem of distinguishing realizable from very random or very scattered samples. And the second result I'll describe is about learning intersection of half spaces. Here I remind you that the best known algorithms are unable to learn even intersection of two half spaces, whereas the best known lower bounds only rules out learning intersection of polynomially many half spaces. And here, under the strong random CSA assumption, we show that learning intersection of any super constant number of half spaces is hard. And we have several more results that I won't describe. So essentially, we get all the results that are known to hold in using the cryptography technique. We can get them using our new technique and more. Okay, so let's summarize and describe what we plan to do next. So we show a new technique to prove lower bounds on learning problems. And I think there is much to do about the basics on these techniques and about applications of these techniques. So maybe the most important problem comes from the fact that the assumption we made is strong, and we want to prove the lower bound I presented here based on weaker or simply different assumptions. And I think that we have a good candidate, which is the following assumption. So this is the strong random C assumption restricted to K-SAT predicates. So we assume that for every D, there is K, think again about K as much larger than D, such that it is hard to distinguish satisfiable from random k-sat formula with n to the d constraints. So again, all the evidence we've talked about regarding our assumption holds for this assumption, and the difference is that this very concrete problem has been studied a lot, and the performance of the best known algorithms is very, very far from what is predicted by this assumption. And I'll say that with a little hesitation, but we think that we had a little progress last week, and we think we know to prove the result I've mentioned before based on this assumption. Okay, so hopefully in a few weeks it will be in there. And lastly, another family of natural open question is to use our new technique to prove more lower bounds. So even if you're willing to assume the strong random C assumption, there are still learning problems, still interesting learning problems that we don't know to prove that are hard, and we think that are hard. And these are maybe the three most interesting, at least in my opinion, such problems. So the first is the problem of learning decision trees. The second is the problem of learning intersection of constantly many half spaces, maybe even two half spaces. And the last problem is about agnostic learning, is to show that it is hard to learn half spaces in the agnostic model with a super constant approximation ratio. Okay, so here I'll finish. Okay, it's a good question. Okay, so the question was, the point of this work that it is hard to rule out improper learning. And a basic question whether there are problems that we know to learn improperly, but we don't know to learn properly, right? Yes, improperly. Yeah, okay. So there are such problems. There are even interesting such problems. For example, learning 3 DNF formula that we don't know to learn properly, and we know that it is NP hard to learn by a proper algorithm, but these problems can be learned by an improper algorithm. So there are several such problems. So this is a real problem. Thank you.